Okay, today I'd like to just finish up a little bit of material in the end of Chapter 2 and then spend most of our time on the Chapter 3. Are there any questions, though, up until this point? There's no homework assignments due today, so maybe there's not very many questions. That's usually the pattern. All right, so remember the three parts of the C memory model. Global variables are stored where? Fixed location in memory. Local variable, locals and parameters on the runtime stack. And the third one, which we're just going to do very briefly now, are dynamically allocated variables, which are allocated from the heap. Now, a lot of you guys have programmed in Java and in C++, and when you allocate storage from the heap, it's the operator called new, N-E-W. In C, the equivalent of new is not an operator, it's a function called Malloc for memory allocation. So it's Malloc, you execute Malloc to allocate from the heap, and then what was it in C++? How did you deallocate from the heap?
Delete.
It was delete. So here again in C, it's a function called free. So Malloc and free correspond to new and delete. And so just like with new, and I assume you've done pointers before, in C, Malloc allocates a memory cell from the heap large enough to hold a value of the type that is on its right-hand side, so you have to specify the type. And then it returns a pointer to the newly allocated storage. And then I assume you know how pointer assignment works. If you say P gets Q, that makes P point to the same thing that Q points to. So that's pointer assignment. And here is a little nonsense program to show how it works. And notice that what happens is in C, instead of saying A gets new int, you say, it's a little more, the syntax is a little more cumbersome. You say A gets parentheses int star, so it gets a pointer to an int, and then you call Malloc to allocate enough storage for an int. So you say Malloc and then size of and then int. So it's just a little cumbersome, but that's the same thing as doing a new. And then star A, if A is a pointer to an int, then what is star A? It is the integer that it's pointed to. So that the pointers work the same way in C as they do in C++. So star A is the star in star A gets 5 is the dereferencing operation. And then B gets int star Malloc size of int, and then star B makes the thing that B points to, gets 3. And now when we say C gets A, what does that make happen? Makes what point to what?
C points to
C doesn't quite point to A, it points to the same thing, what? That A points to, okay? And then so on with this example. And here in figure 2.39 is a sequence of the operations in that program from the previous slide. So the initial, let's see, what was it initially? A, B, and C. What are A, B, and C? Are they local or global? Here in figure 2.38. They're global because they're outside main. And so when you say int star A, that means A is a what? Pointer to an int, right? So where are globals stored? A fixed location in memory. So do you see why in figure 2.39 the A, B, and the C are out there in a fixed location in memory? They're not on the runtime stack. Are you with me? And then A gets Malloc, etc. So A, that allocate storage from the heap, and then star A gets 5 in part C of the figure, the cell that A points to gets 5, and then we allocate storage for B in part D, and then in part E, star B gets 3, so that makes the cell that B points to get 3, and etc. And so, and by the way, so what happens if we do C gets A? What did we say that makes happen? C does what? Points to the same cell that A points to, so that's pointer assignment, and etc. It's a little nonsense program just to show how pointers work. Then in figure 2.40 is a struct. So a struct is like a class, but usually without, well, there are no classes in C. C is not object-oriented. But a struct in C is like a class, well, it's like a struct in C++. And a struct in C++ is like a class in C++, but there are no methods. There are only attributes. So that's struct person is named person, and so we have char first, char last, int age, and other, char gender. So 2 characters and an integer. And some code there to show how to access the parts of a struct with the dot notation. And then here's a little run of the program in figure 2.40. BJ32M, the output is initial, it reads the input and just echoes it. Initials BJ, age 32, gender male. And in figure 2.41 is how you normally use pointers to, how you use a struct to combine a pointer with a data element, and then that pointer part of the struct is a link to another node. So this is how to do linked lists. You guys have all done linked lists before, right? I assume you have. Okay, so here, oh, by the way, before we look at the figure, in this particular program, in figure 2.41, what is value? Is it local or global? It's a local, and it's a local what? It's a local variable, it's a local integer. So where is it allocated? On the what? On the runtime stack. So let's take a look in figure 2.41. We said that value is a local int. What about first? Is first local or global? It is local because it's declared inside main. And what is its type? It is a what to a what? It's a pointer to a node. And a node has how many parts? 2 parts, a data and a next. And what is the type of next? A pointer to a node. Okay. So what this program does is there is a list of integers for the input in figure 2.41, the second part of the second slide. The integers are 10, 20, 30, 40, and then minus 9999. So that minus 9999 is a sentinel to tell the program when to stop entering the input. Yeah, question?
Yeah, so for the struct node, because...
Yeah, that's a good question. Notice that when it says struct node, it's not a variable, so it's not allocated at all. It's just defining. Nothing is allocated. When the compiler gets to struct node and it translates that, it just stores the information of the structure that it will need when later on another variable is declared to be a struct, either a node or a pointer to a node.
So where does it store the information of like what's in it? Like on the runtime stack? Or
No. It stores that's a good question. We will see. Yeah, but it stores it in an internal table in the compiler. You see what I mean? It's not stored during runtime. It's the information about struct node is stored in a table inside the compiler. It doesn't allocate storage for it during runtime, during the execution of the program. That was actually a really good question. You understand? You see what the concept is? The compiler itself has to have the information about node, and it stores it in an internal table in the compiler, but that's only to be used during the translation process. Do you see how that? Yeah, question?
Would it also store like classes in that internal table?
Yes, that's a very good question. In an object-oriented language, there are tables that store all that, all the information about classes. Yeah. Yeah, these are good. These are really good questions. You have another one?
And like in that, and
a pointer to they would be translated, and a pointer to them would be stored in the table. The question is, where are the methods stored in an object-oriented programming language when you define a method? And the answer is, the compiler has to translate those statements for the method, and then what it stores is a pointer to the first statement of the method to be executed when it gets executed.
And does it store that on the runtime stack, or that?
No, that's not stored on the runtime stack. The runtime stack is used for storing things during the program execution. See, we're going to see this in detail, but anyway, let's make a major point that your question brings up. There is a huge difference between translation and execution. Which one happens first? Translation happens first. And we're going to see how these are such good questions for us to, because this is the heart of how a computer system works. And then in figure 2.42, there's this series of snapshots about what happens during execution. Do you see what we're saying? During execution. So in part A, the variables are locals. The variables first, P and value, are local, so they're on the runtime stack of the main program. And you can trace that through. All right? All right. Now, so we're going to spend most of our time today, the rest of our time today, on chapter 3. And the topic is information representation. Now, here is what we have to be super aware of. Have you memorized these 7 levels yet? Here, shall we turn it off? What are the 7 levels? Application. App 7. High order language 6. Assembly level 5, ASMB 5. Operating system 4. Instruction set architecture, ISA 3. Microcode 2. Logic gate 1. We now in chapter 3 are describing information representation at what level? ISA 3. What is the language at ISA 3? Every level has a language. What is the language at level 3? Both for information and for programming. What is it? It's binary. Bits is right. It's binary. Is everybody with me on this? We already saw how information is stored in binary in chapter 1. Now we're going to see how we do operations on them. Now here's the thing. In a computer system, information is stored always in a group of sequential bits. And what we have here in figure 3.1 is an example of a 7-bit cell. And these cells can range from 4 bits, 2 bits, 7 bits, 8 bits, 32 bits. There are different parts of the system store different widths, different numbers of bits for the binary information. Do you see what we're saying? So we have to be able to deal with how much information can be stored in a cell with an arbitrary number of bits. Are you with me? This is just an example in figure 3.1a of a 7-bit cell. Now what can be in that 7-bit cell? In part B of the figure, these are some possible values. Each bit is either a what or a what? A 0 or a 1. So here are some possible values in the 7-bit cell. Right? By the way, how many possible values can be stored in a 7-bit cell? We saw that in chapter 1. What was that? 2 to the 7. 2 to the 7. 2, 4, 8, 16, 32, 64, 128. 128 possible values can be stored in this 7-bit cell. Here are some impossible values. The first one is digits. Decimal digits. You can't store a 6. You can't store the letter J in one bit. And in the last one, you can't store nothing. You can't store nothing. It has to be something. So there will be a value. In other words, it's impossible for a bit to have yet a third. It's impossible for a bit to have a third value that is empty. It will be a 1 or a 0. You might not know what it is, and sometimes we might have a picture of a cell that is blank, but when we show it like that, that's really not technically accurate because that value will be something. It will be a 0 or a 1. Do you see what we're saying? You see the point here? Okay. And now, we need to know how to count in these different bases. So let's review how to count in binary and decimal. 1, 2, 3, 4, 5. Sorry, start with 0. Those are the counting numbers. 0, 1, 2, 3, 4. Actually, how many fingers do we have? 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now when you get to 9 and we're counting in base 10, what happens? When you run out of fingers, what happens?
Restart.
With this number, we go back to the 1 and we make that a 1 and a 0. Now do you see that pattern? And then 1, 1, 1, 2, 1, 3, 11, 12, 13, 14. And when you get up to 1, 9, it's what? 2, 0. Okay, so everybody, you've seen this pattern all your life. And what would happen if we were born with just 8 fingers? We would probably be counting in base, instead of counting base 10, we'd probably be counting base what? So what would the numbers be? 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7, and if it's base 8, what would you write down for 8? Because you ran out of fingers, so what would you be?
1, 0.
1, 0. So this would be 1, 0. What was the next one? 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. Now what would the next one be? 2, 0. Good. So does everybody see how that's counting in octal? Okay, in some computer systems, it's important to be able to count. They represent quantities in octal. So you see it's 2, 0, 2, 1, 2, 2, and then it goes up to 3, 7. What's the one after 3, 7? 4, 0. So everybody see how that works? What about if you only had 3 fingers? Base 3, what would it be? Let's count. 0, 1, 2, but now what? 1, 0, 1, 1, 1, 2, wait. Oh yeah, 2, 0, 2, 1, 2, 2, but now after 2, 2, what would it be?
3, 0.
Oh no, 2. 1, 2, 0.
1, 0, 0, yeah. Now, is everybody clear on that? Does everybody see how that works? So here it is in counting base 3. 0, 1, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2, 1, 0, 0, 1, 0, 1, 1, 0, 2, 1, and look, what's the one after 2, 2, 2? 1, 0, 0, 0. All right, are you ready for this? Let's count in binary. All right, you tell me. 0, 1. Oops, we already ran out of fingers. What's the next one?
1, 0.
What's the next one? What's the next one?
1,
Up. Yeah. 1, 0, 0, right? Don't peek. Next slide.
1, 0,
No, not 1, 1, 0.
1, 0,
1, 0, 1. 1, 1, 0. 1, 1, 1. Now what's the next one?
1, 0, 0, 0.
1, 0, 0, 0. 1, 0, 0, 1. 1, 0, 1, 0.
1, 0.
Not 1, 1.
1, 0, 0.
1, 0, 1, 1. Now what?
1, 1, 0, 0.
Not 1, 1, 1, 1.
1, 1, 0, 0.
1, 1, 0, 0.
1, 1, 0,
1, 1, 0, 1. 1, 1, 1, 0. 1, 1, 1, 1. Now what? 1, 0, 0, 0, 0. By the way, this is not 10,000. What is it? In fact, this is not 10,000. What is it? Well, if this is 0, 1, this must be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. What number is this? 16. Are you with me? So here's how you count in binary, and so on. So you need to know how to do this. We need to know how to count it. Does everybody see the pattern? All right? You need to know how to count in these various bases. All right, so that's counting in binary. Now, how can you figure out, if you have a pattern like here on the screen here, we have 1, 0, 0, 1, 0, 0. So here, one of those numbers is 1, 0, 0, 1, 0, 0. Now, one way to figure out the number, this number in decimal would be just to write it out until you get to that number and then just go 0, 1, 2, 3, 4, 5, 6, like we did before. But if it's a really long number, you won't have time to do that. So how can you figure out what this number is? The decimal. We're talking about, by the way, we're talking here about unsigned numbers. There's two ways to store an integer, signed and unsigned. Unsigned means what? Natural numbers, 0, 1, 2, 3, 4, all the way up to the max. Are you with me? So if this is an unsigned number, what is its value? How can we know what its value is without without just laboriously counting all the way up to
It's like 1, 2, 4, 8.
Yeah, exactly. So what happens is, in figure 3.2, we see that in binary, the place to the left is the ones place, and then this is the twos place, the fours, the eights, the 16s, and the 32s. Do you see how that works? Because, and it's analogous to decimal. See in figure 3.3, the 58036, the 6 is in the ones place, the 3 is in the tens place. So each place is what? In decimal, each place is what compared to the previous one? 10 times more. But in binary, each place is what? 2 times more than the previous place. Is everybody clear on that? It's all just analogous. That analogy is a good thing. So therefore, what would this number be? Well, we just have to count up the places, right? So this is what? 0, oh no, sorry, this is the ones place. 2, what is this? So this would be 4, no 8s, no 16s, plus what? What's this one? 32. So that would be 36. So this number is 36 decimal. So the way we write this, the way we write that, our notation is going to be like this. 100100, and we'll say bin equals 36 decimal. That's how we'll notate it. All right? Is everybody clear? But now how about going the other way around? Oh, in figure 3.2 there's an example converting to decimal. Now how about going the other way around? Suppose you have a number like this. Now, suppose you want to go the other way around. Like suppose we have a number like, I don't know, let's just say, pick a number.
5,000.
Well, not 5,000 is too big. Come on, give me a break. 57. Okay, 57 is the number. Now, so watch what you do. You successively, okay, you put the number here, the 57, and you successively divide by 2, and you put the quotient here and the remainder here. Now, when you divide a number by 2, what is the remainder going to be? It's either going to be a what or a what? A 1 or a 0. So what is 57 divided by 2? What remainder what? Oh, come on.
28.
It's 28, remainder what? 1. Remainder 1. Does everybody see? And then what's the 28 divided by 2?
14.
Remainder 0. So this is 14, remainder 0. 14? 7, remainder what? 7. 3, remainder what? 1. 3? 1, remainder 1. 1? 0, remainder what? 1. Now you're done when you get down to 0. And now answer me this. Riddle me this, Batman. What is the number? Is it 111001 or is it 100111? Is it, do you read it down or do you read it up? How can you figure that out? Well, look. How do you know if a decimal number is even or odd? What digit do you look at? You look at the last digit. And if the last digit of the number is even, the whole number is even. And if the last digit is odd, the whole number is odd, right? What do you think it is in binary? You look at the last digit. If the last digit is what? 1, it is what? Odd. And if the last digit is 0, it is even. Now that's an important fact. Is everybody Clear on that? That's how you tell whether a binary number is even or odd. All right, now tell me, which number are we generating here? Is this the last, is this the digit on the right? Is this the least significant one? Or see, look, if this number were even, what would this digit be?
A 0.
A 0. But if this number is odd, this is going to be what? If this number that we're converting is odd, what will this digit be? 1. And if this number is even, what will this digit be? 0. So do you see that this is the digit, this is the bit that is telling us whether it is even or odd? Now does everybody see that reasoning? This is the bit that's telling us whether it's even or odd. So that means that we have to rewrite it this way, 111001. So what this tells us is that 57 decimal equals 111001 binary. Now, does everybody see how that worked? Are we good? So here I think we have an example with, in figure 3.4 is the polynomial representation. All right, so you know the place value is the base raised to the power of the position in the number. And here's an example of converting 22 from decimal to binary, like we just did. So what is 22 in binary? Yeah, right, 10110, reading up. Is everybody clear on how that works? Remainders, dividends. All right. Now, next question is, how do we do operations in binary? Because what happens is, in the central processing unit of the computer, that's where all these operations take place, and one of the most common arithmetic operations is addition. So we need to figure out how to add in binary. Now do you see on this slide the binary addition rules? 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1. And what happens if you take 1 plus 1? It's 2 in decimal, but that's 10 in binary. Are you with me? Now look, you guys. Now we have to understand how to add in binary. So watch this. And anytime you do an addition of two quantities in binary, you have to know what the cell size is. Because, we don't have infinite precision in a computer. Everything is finite. So there's always a finite set number of bits. So we have to determine, so anytime you do an operation, you will always know what the size of the cell is in bits. So let's do something, I don't know, let's do a 6-bit cell. So that has to be specified for the problem. All right? And anytime, now that we know that it's a 6-bit cell, we have to put all leading, you have to write down 6 bits. So all quantities have to have 6 bits in them, including the leading zeros, if any. Are you with me? So watch this. Let's add some quantities. 0, 0, 1, 1, 0, 1 plus 0, 1, 0, 1, 1, 1. Let's add these two quantities. So here is add. All right. So it's the same way as we do addition in decimal. 1 plus 1 is what? 1, 0. So you write down the what? And carry the what? 1. Now, did everybody see that? A lot easier. You don't have to remember, what's 7 now? What was 7 plus 9? You don't have to remember all those rules. It's just one. Okay. And now, what is 1 plus 0 plus 1?
0. Or 1, 0.
Yeah, 1, 0. So you write down the what?
0.
It's 0, carry the what? 1. 1 plus 1 is what? 1, 0. Plus another 1 is what? 1, 1. Write down the what?
1.
Carry the what? 1. What is 1 plus 1 plus 0? 1, 0. Carry the 1. What is 1 plus 0 plus 1? 0, carry the 1, and notice 1 plus 0 plus 0. 1. Now, does everybody see how that? Oh, this was not a good example because I had to carry on every single one. Anyway, you get the idea. Yeah, question?
If you had gotten yourself into a situation where, like, it would have been a 1, 0 at the end, you're store it.
That is a really good question. That's the next point.
Great.
The question is, what would happen because in this particular example, we didn't have any carry out from the leftmost bit, the leftmost position. And the answer is, get this, there is a special bit in the CPU. It is called the carry bit. And we're going to denote it by the letter C. And it is an extra little bit in the central processing unit such that every time you do an operation, the carry out is stored in that bit in the CPU. And it's called the carry bit. So to be technically complete with this one, when we did this addition, C equals what? 0, because there was no carry out from here to here. Now, does everybody see how that worked? And that's how the software, after an operation, can tell if it did an overflow.
And it would never need to carry more than the 1?
Right. It would never need to carry more than the 1. Because the worst it could be here would be 1, 1 here and a 1 here, and that's 1, 1, carry the 1.
What if you were adding 3 numbers?
Well, you do them 2 at a time.
So it'd be a carry bit.
Well, then the software, what we have is we have instructions in the instruction set at the ISA 3 level that are able to test the carry bit after and it's up to the software as to whether or not you want to test that carry bit after each one. But in the hardware, if the carry is out, it just stores it in the C bit, and that's what the hardware does. Yeah.
Can you add 2 different cells of different bit size?
No. The question is, can you add 2 different cells with 2 different bit sizes? The answer is no. So what you have to do in that situation is you normally extend the short one to be as long as the long one, and then add those 2 of equal size. So that's called extension. So you can't extend yeah, and that does happen. In computer organization, we see that happening a lot. If you ever take that class, yeah. So is everybody good with this? Now let's make sure that this works, that this addition worked. What is this number in decimal? What place is this? 1 plus what? 0 plus what? 4 plus 8. Somebody do 1 plus 2, 8 plus 4 plus 1. What is that?
13. 13.
What is this? What's 1 plus 2 plus 4 plus 16? Somebody do that quick. 23?
Yeah. 1 plus 2. Yeah. 7, 23.
Is that right? Do we have agreement? Now what is, let me see, 1, 2. What is 4 plus 32? 36. 13 plus 23 is 36? Son of a gun. Now, does everybody see how that works? Okay, so now all of that, oh, by the way, so all of that addition in binary is all for unsigned numbers. Are you with me? This is for unsigned numbers. Is everybody clear? Actually, since we brought up the C bit, there's 2 more bits that we can look at now. There's another bit called the Z bit. What do you suppose Z stands for? Stands for 0. Because look, it would be possible for you to add 2 numbers and get zeros here with a carry out. Or you could get zeros here without a carry out. If you add 0, 0, 0, 0, 0, 0 plus 0, 0, 0, 0, 0, 0, you get zeros. And this Z is a 1 if the result is all zeros. So in this case, this is not all zeros, so Z equals 0. There's a slide coming up that'll summarize this. Anyway, that's just an example of another bit called the Z bit. All right, now the next question is, suppose we have a 1, 2, 3, 4, suppose we have this 6-bit cell, and we want to store -5. Now we are talking not about unsigned numbers, but signed numbers. How do we store negative numbers? Now this is really interesting. Because in decimal, how do you write down a -5? You put a hyphen, and then you just write down 5. But look, here in figure 3.7, can we write hyphen 00101? Because what is 101?
5.
By itself, it's 5. So can we put hyphen 00101? No. Because hyphen, you can't, each cell has to have a what or a what?
1 or 0.
A 1 or a 0. So what do you suppose we do? Instead of putting hyphen, what do you suppose we do?
Put a 1.
Put a 1. So a 1, so what you do is you reserve the first bit to be what's called the signed bit, and you put a 1 if the quantity is what? Negative, and you put a 0 if the quantity is what? Positive. Non-negative. Are you with me? So how do you suppose -5 is stored? Instead of being hyphen 00101, what do you suppose it is?
1.
1.
Yeah. You would think it would be 100,101. You would think, but you'd be wrong. It's not stored that way. It is not. Now it is true that to store signed numbers, the first bit is a signed bit, and if it's a 1, it's a negative, and if it's a 0, it's non-negative. That is true. But the way you store -5 is not to just put 5 in the rest of the bits and then just put a 1 to make it negative. That part is not true. It is not the case.
Is it a thing about like scrolling back?
Yeah, it has to do with the pattern. Actually, here's the thing. Do you see that what you want to do is in the CPU there's going to be circuitry that adds 2 numbers in binary. Are you with me? And what you want to have happen with that circuitry is you want to have that addition circuitry be such that if you add 5 and -5, you want to get what? 0. If you store it with a 100,101 and you add those 2 numbers, just sign bits and all, you won't get 0. Do you see what I mean? So here's the question. So we want to store -5, right? So now we know what's positive 5. What would positive 5 be? 000,101. So that's positive 5. 000,101. Are you with me? And the question is, now see if you can work this one out. There's a little puzzle. What string of zeros and ones here, what binary digits should we put here, what bits should we put here, such that if we add it to this, we get what? All 6 what? All 6 zeros. Because if we get all 6 zeros, then there will be a 0 in the sign bit and the quantity will be 0. Now, do you understand what the puzzle is? So let's work it out. So what would have to go here?
1.
A 1. Now, but if we add 1 plus 1, what will we get? We'll get 0, and we will carry the what? The 1. But now what has to be here? There has to be a 1 here, because we need to get 0 here. Do you see? Because if this were 0, what would it be? 1 plus 0 plus 1, we'd get a 1 here. Are we good? So does everybody see? This has to be 1. So if we add 1 plus 0 plus 1, that's 0. Carry the 1. Now what would have to be here? 0. Are you with me? And now, so because 1 plus 1 plus 0 is 1, 0, carry the 1. Now what would have to be here? 1. So 1 plus 0 plus 1 is 0. So what would have to be here? 1. 1 plus 0 plus 1 is 0. Carry the 1. And what would have to be here? 1. So 1 plus 0 plus 1 is 0. And what would happen? C would be what? C would be 1. And what would Z be? Ah, is this all zeros? Oh yeah, you're right, 1. So here's what our, hold on one second. So here's what our conclusion is. Our conclusion is this is the quantity that you have to add to positive 5 in order to get all zeros. So this number must be what? Negative 5. This must be how negative 5 is stored. Are you with me? Does everybody see that? So what did we say? We said, so what we're saying is this. We're saying 1, 1, 1, 0, 1, 1, binary equals negative 5 decimal. Now, you don't have to go, there's a rule, there's an algorithm for doing this conversion without having to do this bit by bit. And what is it? Okay, in figure 3.8, for signed numbers, we have a magnitude. We have the sign bit in the first location and the magnitude in the remainder of the bit positions. And now to explain how the algorithm works, there are two operations that we have to know about. Neg and not. Now what does neg mean? Negative. It means negate. Are you with me? So another word, another phrase for negation is called taking the two's complement. That's another phrase for negation. And the not operation is doing what? What does it say here on the slide? Change all the what? Ones to zeros and zeros to one, because not true is false and not false is true. So it's like true and false. We'll see here in a minute. Are you with me? And the rule is this. The two's complement rule, in other words, how to negate. When you say take the two's complement of a signed integer, what are you saying to do? When you say take the two's complement of a number, what are you saying to do? Negate it. Find its, negate it. Turn it into its negative. Are you with me? So here's the rule. The two's complement of a number is 1 plus its one's complement. Now what is its one's complement? That's the negate. See? So neg x equals 1 plus not x. So look, here's how it worked in this particular example. So what did we say 5 was? 5 decimal? What is 5 decimal? 000101. So yeah, that's 5. And so now, tell me. And so what does this rule say to do? What does it say to do? It says neg x equals what? 1 plus not. So what's the not of this? How do you take the not of this? It's 1, 1, 1, 0, 1, 0. Does everybody see that this is the not of this? And then what do you do to this? Add 1. So you add 1. And so that's 1, 1, 1, 0, 1, 1. And sure enough, this is this. Now why does that work? Because look, if you take this number and you make every 1 0 and every 0 1, what are you going to have? This would be what? I mean, if you just negate this one, what would this be? 1, 1, 1, 1, 1, 1, 1, 0, 1, 0. And if you added that, what would you get? All what? All ones. And then if you add 1 to all ones, that's going to turn them into what? All zeros with a carry out. You see that pattern? Are you with me on that? Okay. So this is negative 5. You flip the bits, you add 1, that's how you negate a number. Now if this is going to work, what should happen if you negate this one? What should happen if you negate negative 5? What should you get? You should get positive 5. Well, let's try it. Because if this really works, if you negate this, okay. So how would you negate this? Flip all these to what?
0, 0, 0.
So invert. So 0, 0, 0, 1, 0, 0. So that would be 0, 0, 0, 1, 0, 0. And then do what? Add 1. And what do we have? 0, 0, 0, 1, 0, 1. And sure enough, voila! This is positive 5. Is everybody clear on how that works? Oh, here, let me do one example with negatives. Let's add -2 and -3. And what should we get? -5. So now so we need to know how to write down, how do we write down -2? So what is 2? So here's -2. How do we write down -2? What is 2? Well, in a 6-bit cell. What is 2? 0, 0, 0, 0, 0, 0, 0, 0, 1, 0. That's 2, right? So how do we write down -2? 1, 1, 1, 1, 0, 1. Add what? Add 1. So this is what? 1, 1, 1, 1, 1, 0. I think because 1 plus 1 is 0, carry your 1, right? And then 0, 0, 0, 0, right? So everybody see that this is -2. So here's, and notice what's in the sign bit. 1 in the sign bit, as it should be. Are we good? So here's the -2. 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 0. And what about -3? Let's do -3. So now what is positive 3? 0, 0, 0, 0, 1, 1. All right, and then what? And then what do we do? And how do we make -3 out of this? 1, 1, 1, 1, 0, 0, and then do what? Add 1. So that becomes what? 1, 1, 1, 1, 0, 1. Is everybody clear? So this is -3. So this is -2. This is -3. So here's our -2. Now -3 is what? 1, 1, 1, 1, 0, 1. 1, 1, 1, 1, 0, 1. All right. Let's add them. What do we get? What's 0 plus 1? Carry your what? 0. Yeah, carry nothing. Now what's what? 0 plus 1 plus 0? Carry what? Nothing. 1 plus 1 is what? 1, 0. So you write down what? 0, carry the 1. Now what? I think it's 1 carry the 1. 1 carry the 1. 1 carry the 1. 1 carry the 1. So what is C? 1. Oh, hey! Isn't this -5? Ta-da! It works. Does everybody see how that works? But now here's the thing, you guys. This is correct, even though we had to carry out. So now with unsigned numbers, with signed numbers, the C bit no longer tells us that we are out of range for the summation. So guess what we have to have? Another bit called the V bit. And in this case, the V bit is 0 because we added -2 plus -3 and we got -5 and we are in range. And so there was no overflow. So V stands for signed overflow. So here are the bits. Here are the status bits. N equals 1 if the result is negative. So what would N be on this one? It's a copy of the sign bit. So you see, so here N would be 1. All right? So N equals 1 if the result is negative, N equals 0 otherwise. Z equals 1 if the result is all zeros, Z equals 0 otherwise. V is a 1 if a signed integer overflow occurred. V equals 0 otherwise. So you see, V, this it's okay to add -2 and -3, and this is -5. And so V is 0 because there was no overflow. Hold on. And then C equals 1 if an unsigned integer overflow occurred, and C equals 0 otherwise. Okay, now question?
N stands for negative.
The hardware has both, and the software, and so they are both set whenever you add two binary quantities. And the hardware can detect either one. But the software can detect either one. Okay, we're a little late. Sorry. See you on, but anyway, you have some exercises dealing with this stuff. And we'll see you on Thursday.